Welcome back to G Fun Facts Online. Today we are diving deep into a materials science breakthrough that has effectively solved a puzzle standing for over 2 decades. We are talking about the creation of atomically thin metals, a feat achieved through a new technique called van der Waals squeezing. To understand why this is such a massive deal, we first need to look at the landscape of the two-dimensional, or 2D, world. Since 2004, when graphene was first isolated by peeling carbon layers off graphite with Scotch tape, we have witnessed a revolution in materials. That discovery proved that materials could exist in a single atomic layer, sparking a gold rush into what scientists call flatland. Over the years, the 2D family grew rapidly. We found semiconductors like molybdenum disulfide, often used in transistors. We found insulators, like hexagonal boron nitride, known as white graphene. We even discovered magnetic 2D materials. But there was a glaring hole in this periodic table of flatland. Pure metals were missing. You might wonder why. We have metals everywhere in our 3D world, so why is it so hard to make a flat 2D metal? The answer lies in atomic bonding. Materials like graphite are naturally layered. They are like a deck of cards held together by weak van der Waals forces. It is easy to slide one card, or one layer, off the deck. Pure metals, however, are completely different. They are 3D crystals held together by a non-directional sea of electrons. Metal atoms want to be surrounded by neighbors on all sides. When you try to thin a metal down to a single atomic layer, the laws of thermodynamics fight you. Surface tension takes over. The atoms instinctively clump together to minimize their surface energy. Instead of a flat sheet, you get isolated islands or nanoparticles. For years, every time scientists tried to grow ultra-thin metals, they ended up with polycrystalline messes, or films that were chemically bonded to the substrate, destroying their free-floating nature. A true, freestanding, atomically thin metal was considered by many to be impossible. That changed in early 2025. A research team led by Professor Zhang Guangyu at the Institute of Physics, Chinese Academy of Sciences, published a paper in Nature that shattered this barrier. They realized that if you cannot grow the metal atom by atom without it clumping, you have to force it into submission. Their technique, van der Waals squeezing, uses brute force and elegant confinement. The concept functions like a molecular vice. Instead of growing the metal, they take a bulk amount, melt it, and mechanically squash it into a 2D sheet before it has time to resist. However, you cannot just use glass slides for this. To an atom, a glass slide looks like a mountain range. You need surfaces that are atomically perfect. The team used anvils made of molybdenum disulfide, or MoS2, monolayers. MoS2 is atomically flat, chemically inert, and has no dangling bonds. The process involves placing a small bead of low melting point metal, like bismuth or tin, between two of these MoS2 anvils. They heat the stack until the metal melts and then apply immense pressure, specifically around 200 megapascals. To give you a sense of scale, that is roughly the pressure you would feel at the bottom of the deepest ocean trenches. Under this crushing force, the liquid metal is forced to spread out laterally. Because the MoS2 walls are perfectly smooth and slippery, the metal glides effortlessly, thinning down until it reaches the ultimate limit, a single atomic layer. They then cool the system while keeping the pressure on, freezing the metal into this 2D state. The result is angstrom-scale metals. They successfully produced continuous single crystal sheets of bismuth, tin, lead, indium, and gallium. The thickness ranges from about 6 to 9 angstroms. If a standard sheet of paper were the anvil, this metal layer would be 100,000 times thinner than a coat of paint. These are not just thin films. They are quantum planes. This brings us to the physics of confinement. Why does squeezing a metal into 2D matter? When you confine a material this tightly, classical physics recedes, and quantum mechanics takes the wheel. Electrons are no longer free to move in 3 dimensions. They are trapped in a quantum well in the vertical direction. This changes the band structure of the material. In a 3D metal, electron energy levels form continuous bands. In an atomically thin metal, confinement splits these into discrete subbands. This can fundamentally alter the material's identity. For instance, bulk bismuth is a semimetal. But in its squeezed 2D form, gaps can open in its electronic structure, potentially turning it into a semiconductor or a topological insulator. Furthermore, this technique revealed a fascinating phenomenon regarding electrical charge, specifically p-type behavior. Usually, when we think of metals, we think of them donating electrons. However, the MoS2 anvils are not just passive containers. They are semiconductors with a high electron affinity. When the high-energy metal layer touches the MoS2, electrons naturally flow from the metal into the anvils. This loss of electrons leaves the metal layer with a surplus of holes, or positive charge carriers. This is significant because creating p-type 2D metals is notoriously difficult. Most metal contacts to 2D semiconductors are n-type, meaning they donate electrons, which creates high electrical resistance, known as the Schottky barrier. These squeezed metals, being intrinsically p-type, could solve one of the biggest bottlenecks in 2D electronics, which is making efficient electrical contacts. Another critical advantage is the interface itself. In traditional manufacturing, you might evaporate hot gold onto silicon. The atoms crash into the surface, creating defects and chemical bonds. In van der Waals squeezing, the metal flows like a liquid over a slippery floor. There are no chemical bonds between the metal and the anvil, only weak van der Waals forces. This preserves the pristine crystalline quality of the metal, allowing electrons to travel long distances without scattering, resulting in high mobility. Let us look at the specific materials they forged. Bismuth is perhaps the star of the show. Monolayer bismuth, often called Bismuthene, is predicted to be a 2D topological insulator. This means it conducts electricity perfectly along its edges with zero resistance, while remaining insulating in its interior. Previous attempts to grow bismuthene required expensive, slow molecular beam epitaxy. The squeezing method produced sheets over 100 micrometers wide, which is gigantic in the nano world and big enough to build real devices. Then there is gallium. Gallium is famous for melting in your hand. This technique exploits that low melting point perfectly. 2D gallium is a prime candidate for 2D superconductivity. The quantum confinement aligns electron orbitals to create flat bands, where electrons move slowly and interact strongly. A recipe for high-temperature superconductivity. We also have indium and tin. These are crucial for the electronics industry. Currently we use indium tin oxide for touchscreens, but it is brittle. An atomically thin mesh of pure indium or tin could be flexible, highly conductive, and transparent, simply because it is too thin to absorb light. This is the holy grail for flexible smartphones and wearable technology. So what does the future hold for this technology? The applications are vast. First, quantum computing. The heart of a superconducting quantum computer is the Josephson junction, a sandwich of two superconductors, separated by a thin insulator. Current junctions use aluminum oxide barriers that are often messy and amorphous, introducing noise that kills the qubit's quantum state. A van der Waals squeezed metal could act as the superconductor, paired with a single layer of MoS2 as the barrier. Because the interfaces are atomically perfect, the resulting qubit could have significantly longer coherence times. Second, post-silicon electronics. As silicon transistors hit their physical limits, the industry is looking at 2D semiconductors. But you cannot get electricity in and out of them efficiently with standard 3D metals. Using a squeezed bismuth layer to inject current lowers the contact resistance by orders of magnitude, enabling ultra-fast, low-power chips. Finally, there is catalysis. In chemical reactions, surface area is everything. An atomically thin metal is all surface. Every single atom is exposed. The unique electronic structure of these strained metals could make them hyperactive catalysts, potentially revolutionizing how we produce hydrogen fuel or reduce carbon dioxide. Of course, challenges remain. Currently, this is a lab-scale batch process. Squeezing one sample takes time. For industrial use, engineers need to develop a roll-to-roll version, perhaps passing metal and 2D films through high-pressure rollers. There is also the frontier of alloys. The initial study focused on pure elements, but imagine squeezing a mix of bismuth and tellurium for energy harvesting, or magnetic metals for spintronics. Van der Waals squeezing is more than just a clever manufacturing trick. It is a conceptual leap. It teaches us that simple materials like lead or tin have secret lives that only emerge when pushed to the edge of existence. By applying pressure, we have not just flattened metals, we have expanded the horizon of physics. That wraps up our deep dive into the world of van der Waals squeezing. Thanks for listening to G Fun Facts Online.